Okay, in the last class, we had seen different examples of how placing zeros in different locations changes the magnitude. And then we had talked about the concept of linear phase filters and group delay. And we argued that having a constant group delay is really important for many types of applications. And then we said that actually, if you just focus on the magnitude response and if you move the locations of the zeros, then you can end up with a case where you don't have a linear phase anymore. So today we want to understand what are the requirements for the zeros of FIR filters if we do want a linear phase. So the goal is understanding the locations of zeros of linear phase FIR filters. And much of what we are going to say today, you can derive these results formally, but rather than doing that, I'll just give you the crux of the results. So as a reminder, what we are looking for is that we have an FIR filter AHN, which has a Fourier transform h of e to the j omega, and we argue that this h of e to the j omega can be written as e to the minus j, or let's call it omega d plus maybe some constant. Okay. So this is the most general form of linear phase systems. There is a constant term which makes it affine, but it's the same case because if you calculate, so your theta of omega is little omega d, which is a constant, plus c. So if you calculate your group delay, which is, so let's put a minus sign here. If you calculate your group delay, which is defined as minus d theta omega by d omega, then you get capital D. So you get a constant group delay. So the question is, what are the requirements if you want a linear phase or a constant group delay like this? Okay. So here is the first condition. In order to ensure linear phase in FIR filters, we must have the following condition. Okay. So if z equal to E naught is a 0, so if I give you the condition that there is a 0 at location E naught, then it should imply something about another 0. So you are going to have another 0. There is another 0 at z equal to 1 over E naught. Okay. So for every 0, you must have another 0 at 1 over E naught. If that is the case, then you end up having linear phase. So let's look at it in terms of the pole zero diagram. So E naught, in most cases, it will be a function, it will be a complex variable. So we'll write that as E naught equal to R times e to the j phi. Right? So you have a 0 at some location, and we'll do different cases, but let's say you have a 0 at here. So this distance is r, and this angle is phi. So the condition says that you must have 1 over E naught must be a 0. Now what is 1 over E naught? Let's write it in terms of, again, polar coordinates. So when you do 1 over E naught, you get 1 over R times e to the minus j phi. So you get another 0 whose distance from the origin is 1 over r. So if you have a 0 inside the unit circle, which means its distance is less than 1, and you take 1 over that, where will be the new 0? So if my r is less than 1, r less than 1 implies 1 over r is bigger than 1. So you have a 0 inside the unit circle, your other 0 will be outside the unit circle. Now if you have the phase phi, then the other thing's phase will be minus phi. So in this example, you will get another 0 here. Okay, this distance will be 1 over r, and this angle will be minus phi. Okay. Now, what if r equal to 1? This means that 1 over r, of course, is equal to 1. So if you have a 0 on the unit circle, if you have a 0 here, for example, so this is your phi, then you will have another 0 on the unit circle, and this will be minus phi. Okay. And of course, the third condition is just the reverse of the first condition, that if I had a 0 outside the unit circle, if I had this figure, I had a 0, for example, outside the unit circle, this is phi, and this distance is r, then I will have a 0 at a minus phi location, and 1 over r, since r is now bigger than 1, 1 over r is less than 1, so I will have a 0 inside the unit circle, but with its angle will be minus phi. Okay. So for every 0, you have to have another 0. If the 0 is on the unit circle, you must have another 0 on the unit circle with the negative angle. If you have a 0 inside the unit circle, you must have another 0 outside the unit circle with the negative angle. And if you have a 0 outside the unit circle, you must have inside the unit circle. So these are only the 3 cases you have. And if you have directions like this, then you are guaranteed to have a linear phase FIR filter. Now in the case of FIR filters that have real coefficients, we can actually impose more conditions on how the zeros can look like. So if an FIR filter has real coefficients, which is what we often desire, then its zeros actually are required to occur in conjugate pairs. And what is the reason for that? That follows from the fundamental theorem of algebra. So an FIR filter has a Z transform which looks like this. Plus PM Z to the minus M. So it's a polynomial with degree M, and now we are saying that the FIR filter has real coefficients, which means that the coefficients of this polynomial are real valued. So the roots of a polynomial with real coefficients, the roots of that polynomial always occur in conjugate pairs. So since this is a polynomial with real coefficients, its roots must occur in conjugate pair. Which means that if z equal to, let's say, ek is a 0, then the conjugate of that, which is ek conjugate, must be a 0 also. So now you can combine the two conditions of you have an FIR filter which you want to be real coefficients and an FIR filter which you want to have linear phase. And if you combine, you get a picture of your zeros which starts looking like the zeros that we saw in the last lecture. Now before that, I just want to pose a trivia question because this will come up. If M is odd, which means that the filter has an even length. So the condition is that if you have a polynomial of degree m, then you have how many roots of that polynomial? So if m is the degree of the polynomial, then we have m roots, which means we have m zeros. And now we are saying m is odd, and we are saying the FIR filter is real coefficients. So from that, what can we deduce? So if m is odd, then we must have at least one real valued root. Because by the pairing argument, we are only going to get even number of roots which are going to be complex valued. So we have at least one real valued root. Now in the z plane, this means that those roots have to lie on the real axis. Okay, so we have a root on the real axis, at least one. Okay, so we'll come back to this point later, but let's combine the two pieces of information that we gathered about. One, we have linear phase filter, and two, we have real coefficients. Okay, so we'll take a few examples. Let's say my first zero, the only thing I tell you is I have a zero at this location inside the unit circle. So my distance from the origin is r and my angle is phi. Just knowing this one zero gives me information about three other zeros because I am saying I have a linear phase and I have real coefficients. So let's talk about the zero that comes due to the linear phase. Because of the linear phase, I am going to get a zero at 1 over r distance, so it will be outside the unit circle and at minus phi location. Okay. But now let's talk about the fact that I have a real coefficient, real valued FIR filter, which means that the zeros have to occur in conjugate pairs. So if I have a zero, so what does conjugation do in the complex plane? it only changes your angle. So it just flips your angle. So if you have a 0 at distance r and angle phi, you have a conjugate pair, which means you have another 0 at distance r and angle minus phi. So this 0 is due to the conjugate pair condition. But you also need a conjugate pair for this 0. So this means that you will have actually another 0 in the same direction, phi, and at a distance of 1 over r. So just by knowing the location of 1, 0, and if I impose the condition that you have linear phase, and you have real coefficients, gives you information about 3 other zeros. I could have given you a 0 for any one of these locations, and you could have filled in the rest of the zeros. Okay. Now, if I had a 0 on the unit circle, so let's say that I had a 0 on the unit circle here. Okay. Now, if this is at distance phi, because of the linear phase, I get another 0 here, and the conjugation condition is also the same. So if I have a 0 on the unit circle, and I give you 1, 0, you know about one other 0 location. Okay. And similarly, if I have a 0 on the real axis, then on the real axis too, for example, if I have a 0 here, now this is real valued 0, so it's not going to have any conjugation, but because of the linear phase condition, you are going to get another 0 at 1 over r. So if I give you a 0 on the unit circle or on the real axis, knowing the location of 1, 0 gives you information about one other 0. If I give you a 0 at any other location in the units in the z plane, then knowing 1, 0 gives you information about 3 other zeros. And if you satisfy this condition, then you are guaranteed that you have number 1, an FIR filter with real coefficients, and number 2, the FIR filter is linear phase. Okay, let's look back at the FDA tool that we looked at in the last class and try to see if we can verify this. So I'll again make some changes which will become apparent later. Right now, I'll just make those changes. So I have, let's say I still work with a low pass filter, and my order, so order means the degree of the polynomial or the number of zeros, so length is order plus 1. So I design this low pass filter, and I get to the pole 0 diagram, and this is what I see. Okay. For every 0, I see a flip version of it, which is, you could either relate it to the conjugation or you could relate it to the linear phase. This pair, this and this pair, is due to the condition of linear phase. So if I go and look at, for example, the group delay, I right now see I have a constant group delay. Okay. If I go and look at the distance, this 0 is at 2.2388 and this 0 is at 0.44668. So they are about reciprocal of each other. I think when I clicked on this, I moved this 0 a little bit. But if I now start moving this 0, you see that now since it's no longer in reciprocal, these two zeros, my group delay is no longer a constant. I no longer have a linear phase filter. Okay. So let's make this simple. Let's make this 0.5. Okay. This is my group delay. And you see that the reciprocal of 0.5, that should be 2. It is at 2.2271. Okay. So this, if I could move this 0 to the location of 2, I will satisfy the linear phase condition and my group delay will become constant again. Okay. These are sort of like artifacts that we'll ignore for the time being. Okay. So these are the conditions, and in this FDA tool you have this conjugation, you have this conjugate radio button that you can click, which ensures that your impulse response is always real valued. You can ask to design a high pass filter with the similar kind of conditions. I'm going to make the cutoff of this high pass filter as 0.75 pi. I'm going to increase the number of zeros. Let's make it 28. And if I go to the pole zero diagram, again you see that symmetric version, which is due to the fact that you have to have both linear phase and real coefficients. So for every 0 on the unit circle, you have a conjugate. You have on the different phase, the negative phase of that. Anything outside the unit circle. So this 0 corresponds to the 3 other zeros. This 0 corresponds to this 0, and this 0. Whereas anything on the real axis or on the unit circle corresponds to 1 0 corresponds to one other 0. Okay. So based upon this discussion, you can actually figure out that your impulse response of your filter always is going to have certain special shapes. And so based upon the length of the filter and the shape of the filter, you can actually characterize linear phase FIR filters into 4 classes or 4 types. And we just call them type 1, type 2, type 3, and type 4 FIR filters. So there are 4 types of linear phase real valued FIR filters. And in all this discussion, I am going to work with n equal to the length of the filter and capital M equals to n minus 1 is the order of the filter or the number of zeros that you have. Different texts use different notation. It is not what letter I use for the length and the order. What matters is that you just understand the relationship of those things. So type 1 and type 2 FIR filter, they are characterized by the shape of their impulse response to be symmetric. So let's look at type 1 FIR filter. The first condition is that it is an odd length filter. It's an odd length filter, which means that it has an even number of zeros. So if the length is odd, you subtract 1, you get even. So that is one condition for it to be type 1, and the other condition is that its impulse response is symmetric about capital M by 2. So if you look at the impulse response, now we are talking about causal filters. If you look at the impulse response from 0, you go up to n minus 1, which is m, and you have m by 2. Now m by 2, because m is even, m by 2 is an integer itself. Okay. So this is going to be symmetric about this m by 2 region. So for example, one of the shapes that you could see will be, I'm just drawing an envelope, will be a filter like this. Or it could be another symmetric shape, which we'll see later. One of the main properties of type 1 filter is that the zeros of type 1 filter are pretty unrestrictive. So it can either have an even number or no zeros at z equal to 1 and or at z equal to minus 1. So if a filter has a 0 at z equal to 1, z equal to 1 corresponds to which frequency? If a filter has a 0 at z equal to 1, that means that frequencies around 0 are pulled down. So a filter which has a 0 at z equal to 1 is not a good filter for low pass filtering, because you want to preserve frequencies around 0. Similarly, z equal to minus 1 corresponds to the frequency of pi. So a filter which has a 0 at z equal to minus 1 is not a good filter for high pass filter. Now type 1 filter may have zeros at z equal to 1 and minus 1, or it may not have. So type 1 filter is the most commonly used filter. It can be used for both high pass and low pass filtering and other types of filters. It's not very restrictive. So we'll once again come back to our FDA tool. We'll say we want to design using the window method with rectangular window. I want a low pass filter with a cutoff of 0.4. And now type 1 filter has an odd length, so its order is even. So I should give any even number, let's say 20. And if I say design filter, it's a good filter, for example, for low pass, and this is what it means in terms of the symmetric response. So my m is 20, so m by 2 is 10. So you see my response is symmetric around n equal to 10. Around m equal to 10, I have a mirror image on the left and the right. It's symmetric around the halfway point. Okay? So an even order filter, which means odd length, and whose impulse response is symmetric, is a type 1 filter. So when I gave MATLAB this command, it generated a type 1 filter. And how do I know it's type 1? Not only by the length of the filter, but also by the shape of the impulse response. Since the impulse response is symmetric, that is what makes it type 1. Now, we can talk about type 2 filter, which is just like the type 1 filter, but with the length being even, an even length filter, which means that n is even And so the order m, which is n minus 1, is odd. Okay. The second condition is the same as the type 1 filter. Its impulse response is symmetric about m by 2. Now note that m is now odd. So m by 2 is actually not an integer. So this means that m by 2 would have no sample itself. So if I look at the shape, and I'm going to stick with the triangular shape, if I look at the shape, I have 0 sample here, I have m here, I have m minus m by 2, m minus 1 divided by 2 is a, and m plus 1 divided by 2 is a sample, but m by 2 is not a sample. Okay. So what it looks like is basically this shape. It is still symmetric, but it's symmetric around m by 2, which is itself not a sample. Okay, so you can't put a sample at m by 2 because m by 2 is not an integer. Now, very small change. You have made the length from odd to even. But this small change actually means a lot in terms of what this filter can do. So the major property of this filter that you should remember is it has either an even number of zeros at z equal to 1 or no zeros at z equal to 1, which means that it can be used as a low pass filter. It is the same as type 1, but the second condition is pretty stringent. It always has an odd number of zeros at z equal to minus 1. Which means that if I tell you I have a type 2 FIR filter, then without any thinking, you can put a 0 at z equal to minus 1. And since z equal to minus 1 corresponds to the frequency of pi, it's not a good filter for high pass filtering. So z equal to minus 1 corresponds to little omega equal to plus minus pi. So type 2 filters are not a good choice for high pass filtering. Okay, so similar to the type 1 and type 2 filter, you have type 3 and type 4 filters. So type 3 FIR filter is very similar to type 1 filter in terms of its length. So number 1, its length is odd. So n is odd and m is even. Okay. So that is very similar to the type 1 case. But what is different is that the impulse response is now, instead of the impulse response being symmetric, the impulse response is anti-symmetric. So its impulse response is anti-symmetric about m by 2. Okay, so if I, and now remember that since m is even, my m by 2 is an integer. So what I get is, if I draw an impulse response for n equal to 0 and n equal to m, I have a sample at m by 2, and it is anti-symmetric. So for example, I'll get an impulse response like this. So length is odd, but impulse response is anti-symmetric. That's type 3. And the condition for, so the property of type 3 filter is the following. That it has an odd number of zeros at z equal to 1 and at z equal to minus 1. So again, you have to relate the zeros to the frequencies. At z equal to 1, that corresponds to omega equal to 0 frequency. So this filter is neither good for a low pass filtering nor for a high pass filtering. So this is not good for either low pass or high pass filtering, and the reason being that it has zeros both at z equal to 1 and z equal to minus 1. Okay. So if your filter is odd length and you see that the impulse response is anti-symmetric, then you know it's type 3. Okay. Let's go to the type 4 filter. And that is just what the relation was of type 2 to type 1. This is an even length filter that is anti-symmetric about m by 2. So what this means is that my n is even and m is odd. So m by 2 is not an integer. So it's anti-symmetric, similar to the previous case, for example, but now my m by 2 is not. So I have n equal to 0, n equal to m. This is an integer, m minus 1 divided by 2, m plus 1 divided by 2 whole divided by 2 is an integer. But m by 2 is not an integer. So for example, you will get something like this, and then you will have to have your impulse response like this. Now this has a condition that the property is that it has an odd number of zeros at z equal to 1 and either an even number or no zeros at z equal to -1. So now with all the discussion, it always has zeros at z equal to 1. So is this a good choice for a low pass filter? So not a good option for low pass filtering, but it can be used for high pass filtering. So if we want to do a sort of quick recap, type 1 filter is good for, is the most versatile. So if n is odd, then we should go with type 1 filter. Is a good option because it is not restrictive. It allows you to either have zeros at z equal to 1 and -1 or no zeros. So it's a pretty good option. Now if n is even, then you should really figure out what kind of a filter you want to work with. For example, if you wanted n even and a high pass filter, then you have two types of filters, type 2 and type 4. Now which one should you use, type 2 or type 4? So you should use type 4 filter is a good option for that if you are interested in high pass filtering. Okay. But on the other hand, if you want n even and if n is even but you want a low pass filter, then which one is a good option, type 2 or type 4? So if you want low pass filter, then type 2 filter is a good option. And if you go to the FDA tool automatically sort of looks at it and tries to give you the best option. So we'll start off with the with the high pass filter design, and we'll say we want a cutoff of 0.6. So our length is odd, which means our order is even. If I design the filter, it looks like a high pass filter. And if I look at the impulse response, it is symmetric. So this MATLAB is giving you now the type 1 filter because you are allowing it to use an odd length. Okay. So this is symmetric around m/2, which is 5. Now let's change the order to 11, which means that now it is either a type 2 or a type 4 filter. But since we are asking for a high pass, MATLAB knows that we should design a type 4 rather than a type 2. So when I now design the filter, I get basically a response which is still acting as a high pass filter. And if I come here and look at my samples, I see an anti-symmetric response. So my M is 11, so this is 5.5. This is the middle. Okay, and you see that around this middle, you have a mirror image of the impulse response, but with a negative sign. Okay, so it's anti-symmetric. So based upon the shape of the filter, which is anti-symmetric, and the length, you know it is a type 4 FIR filter that MATLAB generated. Now if I keep everything the same, but I move to low pass, and I want a low pass filter. Now, a type 4 FIR filter is not a good option for a low pass filter. So which filter will MATLAB now give me? A type 2, which means that it has to be now symmetric instead of anti-symmetric. It will now be symmetric around 5.5. So when I give it this option, I'll just change the view so that MATLAB brings it into the view. And you see that now again, it is giving you a symmetric filter, which is symmetric around 5.5. So there is no sample at m by 2. Okay. So as you go from different options, MATLAB automatically goes from type 1 to type 2 to type 4 and so forth, so that it gives you, this tool automatically gives you the best possible filter that you can have. So since a band stop filter is non-zero at omega equal to 0 and omega equal to pi, you shouldn't use anything other than a type 1 filter, which means your length of the filter must always be odd. So in this toolbox of MATLAB, I tried to generate a band stop filter with a different length. I gave it the command that I want an even length, and MATLAB generated this warning that odd order symmetric FIR filters must have a gain of 0 at the Nyquist frequency. The order is being increased by 1. So MATLAB knows that it's not a realistic goal to design a band stop filter with even length filter. Okay. Because you are going to be constrained to have a 0 either at z equal to 1 or z equal to minus 1, which is not a good option for a band stop filter. Okay, right now we talked about basically determining the length of the filter, and the shape of your impulse response determines what kind of a filter you have, type 1, type 2, type 3, or type 4. You can also determine the same from actually the phase response and length. So the general form of the frequency response of linear phase FIR filter is as follows. These kinds of filters always have the frequency response, which is given by, so you have the magnitude response, absolute value of h of e to the j omega times e to the j minus m by 2 little omega plus beta. Okay. So causal linear phase FIR filters with real coefficients, they always have this form. Their phase response is always of the form minus m by 2 omega plus beta, which means that their group delay is always m by 2. So this is true for all 4 types. And m, of course, is the order of the filter. Now, what determines whether you have type 1 and 2 or type 3 and 4 is through the use of what is your beta. Okay. So if I do even or odd, you are already left with either it's type 1 or type 3 and type 2 or type 4. But can I, instead of looking at the impulse response, look at the phase response? And the answer is yes. So if you have beta equal to 0 or beta equal to pi, then this means that we have type 1 or type 2. And if beta equal to pi by 2 or beta equal to 3 pi by 2, this means that we have type 3 or type 4. So basically, using the length of the filter, you figure out whether you reduce the 4 filters to 2, and then determine based upon whether your phase response has the intercept at 0 or pi versus pi by 2 or 3 pi by 2, you determine whether it's type 1 or 3 versus type 2 or 4. Okay, so you can determine the type of the filter either on the length and shape of the impulse response or on the length and the phase response. That concludes pretty much all the discussion that we needed to have about FIR filters in terms of their zeros, what are linear phase FIR filters, and the different types of FIR filters. And up to this point, we have focused only on basically using the MATLAB FDA tool to determine how do we design FIR filters. Our next goal is basically learning a few of the aspects of the design of FIR filters. So from now, we'll start a new topic, which is design of FIR filters. And we'll focus on only one method, and that is called by windowing method. Okay, so let's just remind ourselves, where does the design of FIR filters come into play? What happens is that based upon the application and the continuous time system that you are working with, you will end up with an ideal filter that you want. So the first step of any design is that you figure out the ideal filter. Doesn't matter if what type it has, ideal filter that we desire. And this filter, most often it will be obtained in terms of the frequency response, but we can compute its Fourier transform to obtain its impulse response. Now, in pretty much all realistic applications, HDN, once you do this step, HDN is going to be of infinite duration. So HDN will be equal to non-zero for n from minus infinity to infinity. The classical example is, for example, the ideal low-pass filter. You figure out what is the response that you want, and when you compute HDN, you get this sinc function which goes forever. So if you have a low-pass filter with cutoff omega c, then we know that our desired impulse response is sine omega cn over pi n for n from minus infinity to infinity. Now we are interested in an FIR filter, and we want a systematic fashion, a systematic framework for getting from this desired impulse response to an FIR impulse response. So we want an FIR filter of length n that is as close to mimicking the frequency response HD e to the j omega as possible. Okay. Now, what we want is somehow systematically convert this HDN into a finite length response. And here I'll use a different notation because your book uses that notation too, so I want to be consistent with that. Let's call n equal to 2m plus 1. So we have a we would ideally want a symmetric filter. We'll call it a type 1 filter. So initially we'll ignore the causality. So what we are interested in is of an FIR filter HT of n, which is equal to 0 for all n less than minus m and n greater than m. Why right now we are not worried about causality? Because it's a finite duration filter. I can always make a non-causal filter causal by shifting it enough to the right. Okay. So this is a filter which goes from minus m to m. If I were to shift this filter by m, I will make it causal. So right now I'm not going to focus on causality. So I am given HDN, which is not FIR. I want HTN, which is FIR. The question is, what should be the relationship between HTN and HDN? The relationship should be based upon their frequency response, because at the end of the day, what we want is that our FIR filter has a frequency response which is as close to the ideal frequency response as possible. So let's call the frequency response of HTN as h of t e to the j omega. Okay. So we want h of t e to the j omega should be close to h of d e to the j omega. And how do we measure closeness? We'll use the metric of squared error, average squared error. So we'll define phi of r equal to, so since these frequency responses are periodic, we only care about going from minus pi to pi. And we take the absolute value of one frequency response subtracted from the other, absolute value squared, we integrate it, and then we take the average of over the 2 pi region. So if ht was exactly equal to hd, then this error will be 0. But in reality, you can't make it exactly equal to 0 because you are constraining the impulse response of this ht to be finite impulse response. So we want to figure out if we want to reduce, want this the smallest. So what does this mean? In terms of HTN. Okay. Now for that, we'll use a property of the Fourier transform, actually two properties. So the first property is the following: ht e to the j omega minus hd e to the j omega. What is the inverse Fourier transform of this? Fourier transform is linear, so what's the inverse Fourier transform of this? So this is simply ht of n minus hd of n. Now, let's call this just some frequency response h tilde e to the j omega. And let's define this to be h tilde of n. Okay. So I am interested in this error phi of r, which is 1 over 2 pi minus pi to pi. I'm just going to write it as h tilde e to the j omega absolute square d omega. I want to write this error in terms of time domain. Any property of the discrete time Fourier transform that helps us relate the frequency domain energy. So this is like computing the energy of this frequency response in the, this is like computing its energy in the frequency domain. What type of property helps us relate the energy in frequency domain to energy in time domain? So Parseval's identity says that this error is equal to actually the energy in the time domain signal n from minus infinity to infinity h tilde of n absolute valued squared. So if I want to reduce this, reducing this is equivalent to reducing this time domain expression. And now I just plug in the values of h tilde m. That is equal to summation n from minus infinity to infinity ht of n minus hd of n squared. Now we know that ht of n is 0 for all n less than minus m and n greater than m. So I can break this summation into two pieces. Summation n from minus infinity to minus m minus 1 hd of n absolute squared. That's the first piece, because in that range ht of n is 0, plus summation n from minus infinity to infinity, from minus m to m ht of n minus hd of n absolute squared, plus the third piece, which is n from m plus 1 to infinity hd of n squared. Now no matter how I pick my ht of n, I cannot reduce this quantity and this quantity, because both of these quantities are not functions of htn. The only quantity that I can reduce is this quantity. How can I reduce it? What is the smallest that this quantity can be? This quantity can be equal to 0 if I make ht of n equal to hd of n for n equal to minus m up to m, then this quantity becomes 0. Summation minus m to m ht of n minus hd of n absolute value squared equal to 0. And you can't make a positive number smaller than 0. Right? So how do you then design an FIR filter from an idealistic filter? Is basically you just chop off all of its pieces from minus m to m. You just keep everything between minus m and m. And we will look at in more detail what's the impact of this chopping off or truncation, or as the term goes, windowing, in terms of the frequency response.